Welcome to Applied Physics with Ms. Hobbs and Mrs. Kleeclamp, and we are going to be talking about electricity and magnets, and specifically how electricity and magnetism are connected with the electric current and magnetism. Later on this chapter, we'll talk about how electric motors work, and after that, we'll maybe explain electric generators and transformers. So later on, we're going to be able to create an electric motor. Okay, and that's going to be relatively fun. And in fact, you've done something similar where we've had those kits with the different colored plastic things that held the batteries, and we coiled wire around it, and then the coil of wire moved with by attracting or being attracted to or repelled to a permanent magnet. And that's actually an electric motor. It creates a current. The current creates an electromagnet. The electromagnetic poles change and loops, and then is attracted to the bottom of the magnet there. So in 1819, Hans Christian Ørsted, a Danish physicist and chemist and a professor, placed a compass needle near a wire through which he could make electric current flow. When the switch was closed, the compass needle moved just as if the wire were a magnet. Now, this is the same experiment that made Michael Faraday so excited, and later on, James Clerk Maxwell. You can see that all the compass needles will point north. And then as you see here, when there's a current, all the compass needles point left in a circuit. So there's something perpendicular to the direction of the current that is making it move the compass needles. And then likewise, when you reverse the current, all the compass needles go the opposite way, just like the poles being reversed like in the electromagnetic lab. Electric current is made up of moving charges, electrons, which creates the magnetic field around a current-carrying wire. Magnetism is created by these moving charges. So we can see there's a magnetic field here that the compasses are reacting to, and there's a magnetic field here that the compasses are reacting to. Magnetic field lines are concentric circles with the wire at the center of the circles. What that means is those that are that loop thing that we've seen so far for the field lines. The direction of the field depends on the direction of the current of the wire. As we can see, when we flip the current of the wire, we flip the field. And you can see those field lines. And those field lines kind of go from the idea of the north to the south pole. They tell us the magnitude of the field. So the field is going to be strongest closest to the wire and weakest further away from the wire. The strength of the magnetic field near the wire depends on two factors. The strength is directly proportional to the current, so doubling the current doubles the strength of the field. The field strength is inversely proportional to the distance from the wire. Decreasing the distance to the wire by half doubles the strength of the field. So as you noticed, when you moved your magnet closer or your electromagnet closer, the reaction to the compass was much quicker. That's because you were decreasing the amount of distance, and so you were moving it closer into the magnetic field, stronger magnetic field. And then on the first one, the strength is directly proportional to the current. So the more current you have flowing, the more electromagnetism you have, and the greater the field too. So near a straight wire, the compass, north pole of the compass needle feels a force in directions of the field lines. So the force itself is not a straight, it's arguably circular in that the way that the compasses behave. And the south pole feels a force in the opposite direction. As a result, the needle twists to align to its north-south axis along those field lines. The magnetic field around a single wire is too small to be much use, and there are two techniques to make the strong magnetic fields from current flowing in wires. Parallel wires can be bundled together. 10 wires, each 1 amp of current, create a magnetic field 10 times as strong as one wire. So that's why we looped those coils and those electromagnets, or excuse me, in those motors, is we were able to make the field much stronger. And a wire can be looped into a coil, so the magnetic field is concentrated at the center. So you'll be able to see the center of where that field is taking place. The most common form of electromagnetic device, a coil, is called a solenoid. The coil takes advantage of these two techniques, bundling wires and making bundled wires into coils for increasing field strength. So we have seen and made these before, and you can see the strongest part of the field is in the center part of the field. and you have these magnetic field lines going out. The closer the field lines are together, that indicates a greater strength. The further away the field lines are, that indicates a weaker amount of strength. And here's another example of a concentric circle, how the circle's kind of bent and heavy. Okay. This is how the coil interacts. So the center of the coil is where our north-south pole is, okay, as well as the permanent magnet works this way. Okay. And then a solenoid is just turned on its side. Two wires carrying electric current exert force on each other just like two magnets. The forces can be attractive or repulsive depending on the direction of both current wires. So in this instance, we've got the current going this way, where the currents are going in the same direction, so the wires are attracted to each other. Whereas if the currents are going in opposite directions, the wires are actually going to repel each other, just like a magnetic field. And that's the end for the 6.1 explanation of how magnetism and coils work.